Hello, my name is Val Kaldarov, and I'm presenting solder joint fatigue studies subjected to board level random vibration for automotive applications. Now, the background, we are participating in a JSG working group that is in the process of updating JEDEC standard JSG 22-B103B. This standard focuses on evaluating electronic components which are used in electronic equipment that are meant for moderate to severe vibration levels and are applicable to transportation and field operations. In this presentation, we would like to focus on the use case that includes autonomous vehicles. Such use case includes longer daily operation hours and mileage, requires strong computing capability and heavy XPU, which includes CPU, GPU, FPGA usage. Compared to thermal analysis, limited work has been allocated so far to high and ultra-high cycle fatigue for random vibration. Such use case also has high cost of bill of material parts and very low life expectancy, about 3 to 4 years for the autonomous vehicles. Therefore, we see a need for reusable electronics at board level, which can then significantly raise the requirement for number of cycles to failure from random vibration. We have been able to identify some of the shortcomings associated with current finite element-based simulations. Popular FEA packages such as ANSYS use so-called Sigelman-Rees algorithm for typical random vibration simulations. Such algorithm, together with Steinberg's 3 sigma rule, can provide only a rough estimate for fatigue life calculations. This in turn necessitates the need to obtain volume average stress response power spectral density to estimate cumulative damage of the solder joint. In turn, this requires an analyst to define an arbitrarily thin volume on a solder ball, which can be very subjective, in order to estimate stress in the solder joint. Packages such as ANSYS, in addition, had difficulties in the past implementing Sigelman-Rees algorithm correctly. Our proposed solution includes a simplified assessment methodology, which is based on vibration tests and FEA, in order to predict high and ultra-high cycle fatigue life of electronic components for random vibration based on a concept of critical plane. Some of the advantages include resulting equivalent stress, having normal distribution with mathematical expected mean equal to 0, which can then make it possible to use Rayleigh distribution for local amplitudes. We have defined 2 test vehicles. It consists of a ball grid array component located in the middle of the printed circuit board. This ball grid array component has a square geometry of 24.5 by 24.5 millimeters, having 769 lead-free SAC-305 solder balls. Now, the first type of printed circuit board is a square geometry, which is 77 by 77 millimeters with 1 millimeter thickness. It is referred to as a small board. The second type is 140 by 140 millimeter square geometry with 1.6 millimeter thickness, which is referred to as a big board. We have conducted vibration tests where we have placed printed circuit board assembly on a shaker that has metal standoffs screwed to 4 corners. We have used an event detector to monitor resistance of the daisy chain circuit. The resistance threshold was set to 1000 ohms in a daisy chain for a period of 1 microsecond or more. We were able to obtain some preliminary test to failure results for power spectral density, which is a flat profile white noise from 10 hertz to 2000 hertz with equivalent root mean square acceleration of 6.27 GRMS. This excitation was given at 4 support locations on the bottom side of the board, which was applied in a vertical Z direction. We obtained time to failure hours for the 2 test vehicles. The Weibull plot on the left shows the purple line, which represents test vehicle 1, which is the small board, and the red line, which is test vehicle 2, which is the big board. We see that the test to failure results for the small board are significantly lower than for the big board. We have been able to obtain Weibull shape parameters for the 2 boards. For test vehicle 1, the shape parameter is 1.5, and for test vehicle 2 is 1.9. These 2 values can be approximated to value of 2, and we know that the shape parameter having value 2 in the Weibull distribution can be used to derive, can be equivalent to the Rayleigh distribution. We then were able to estimate mean time to failure for test vehicle 1 at 6.3 hours, and test vehicle 2 it's 26.1 hours. Now the big difference in the mean time to failure for the 2 test vehicles can be attributed to the presence of 2 different failure modes. If we assume that failure had occurred only in the solder balls, then our hypothesis is that for the small board, the failure has occurred, had a ductile failure, and the big board had a brittle failure. We had collected some measurement results that we had obtained from accelerometers and strain gauges. As can be seen in the figure, we had placed those accelerometers and strain gauges on the top and bottom sides of the test vehicle. From the top side contains 2 accelerometers located at ACC1 and ACC2 location, where ACC1 is placed on top of the package and ACC2 is to the side of the package. And we also placed on one of the test vehicles SG, on both we placed 2 strain gauges SG1, and on one of them we placed SG2, the other one didn't have an SG2, didn't have the strain gauge at SG2 location. Then the bottom side had additional 2 strain gauges at locations SG3 and SG4. We were then able to collect these results and apply a rainflow cycle counting algorithm, which we present as an example for ACC1 location for test vehicle 1. This table can be represented in a histogram, which is shown on the bottom side of the slide. This histogram contains 2 values. One is about 3,000 cycles and the other one is 911. Now the difference is that we had applied a filter in order to obtain 911 cycles. This filter is represented as a vertical line that separates that separates the histogram into two parts. The left part is treated as noise, and the right part is being treated as actual results, which were summed to 911. The same type of algorithm was applied to the rest of the uh, locations, uh, and the histograms and time series are shown on the right side of the slide. From the histograms, we see that there's a big variation in the total number of cycles. For the top side, it varies from for about 5,000 cycles up to 15,000 cycles. However, when we apply a filter, we obtain about 900 cycles, which is comparable to what we had gotten for ACC1 location. From this, we were able to derive parameters. First, we plotted the transmissibility graphs that we obtained experimentally for both test vehicles. We see that for test vehicle one has two natural frequencies, and when test vehicle two has four natural frequencies. The average net cycle counts for all of the locations was 917 cycles for test vehicle one and about 1600 cycles for test vehicle two. From this, we calculated apparent frequency for test vehicle one to be 460 hertz, which is comparable to the natural frequency, the first natural frequency for test vehicle one of 462 hertz. And the apparent frequency for test vehicle two was 1700 hertz, which is comparable to the last natural frequency of test vehicle two of about 1900 hertz. From that, we were able to calculate total number of cycles to failure. For test vehicle one, it was 10.3 million cycles. For test vehicle two, it was 160.2 million cycles. We were then able to calculate overall average amplitudes from the test results. And as can be seen, the average amplitudes were about the same for two test vehicles. We then modeled the two test vehicles using finite element analysis by building 1/4 FEA model that was created with a Sonica M3D package. We applied Nelder-Mead algorithm on model tests for non-JEDEC BGA components and PCB in order to obtain material parameters for modulus of elasticity, Poisson's ratio, and damping coefficients. The equivalent acceleration response values from 6.27 GRMS flat profile were 24G versus 20G for two test vehicles at ACC1 location, and 14G versus 15G for two test vehicles at ACC2 location. Once again, the simulation shows that the two test vehicles have about the same values, which is consistent with the results we obtained from the actual test results. We then show correlation results and prediction for the two test vehicles. The first two plots show scatter points that represent maximum values at ACC1 location for test vehicle 1 and test vehicle 2 respectively. The red line represents the FEA model, and the blue scatter plots represent actual test results. We see that for the first test vehicle, which is the first plot, the correlation results are very good, are very close to each other. For the second test vehicle, which is the second plot, we see we see some offset between the FEA model and the vibration test, actual test results, but the overall trend line is about the same, and we consider this to be adequate correlation. The last two graphs show comparison between vibration test strain values, which were converted to overall average amplitude stresses. So the red line is the FEA, and the blue line it shows the test results from vibration at locations SG1, SG2, SG3, and SG4. So it's for test vehicle 2, and for test vehicle 1, it's SG1, SG3, and SG4. We then used these results in order to predict the maximum stress value at the corner solder ball, which for test vehicle 1 is about 4.4 megapascals, and for test vehicle 2 is about 5.1 megapascals. We also conducted fatigue analysis comparison for SAC 305 solder joints. First, we did some research and found some derived fatigue curves for SAC 305. The first graph shows a stress-based fatigue curve. The red line was derived by the University of Auburn, and the blue line was Binghamton University. Now, the second plot shows strain-based fatigue curve, which contains green line, which was derived by the University of Maryland. Now, if we compare all of these results, we see up to 1 order of magnitude difference. We then compare these results that were published with our own results. We have so far 2 data points. One data point, which is marked X, represents test vehicle 1, and the second data point, which is marked as O, represents test vehicle 2. So we see that from our results, do not follow the inverse relationship between the amplitude and the number of cycles to failure. So if we increase Young's modulus, which was assumed to be 51 gigapascals, to 95.5 gigapascals, the first plot shows a small increase in the stress amplitude. However, the second plot shows that the strain range amplitude would decrease and would follow the inverse relationship between the amplitude and number of cycles to failure. And we see that our results follow closely to the results derived from the University of Binghamton. We also present in this slide a table of summary of estimated parameters. The most important result are shown in the last row for strain rates. The strain rate for test vehicle 1 is much less than 1, it's about 0.25. And for test vehicle 2, we have shown 2 cases, one for 51 gigapascals, which is greater than 1, and for the option where the Young's modulus had increased from 51 to 95.5 gigapascals to 0.63. So from this, we conclude that test vehicle 1 has strain rate which is much less than 1, and for test vehicle 2, the strain rate are close to 1. We were then able to use a simplified model in order to derive a survival function, which is shown for test vehicle 1 and for test vehicle 2 in the two plots. This survival function is shown in the formula, where P is probability density function, T is time, sigma A is allowable stress, sigma is maximum stress value in the solder joint, and F of D is dominant or apparent frequency. From our results, we were able to observe that when the strain rate is less than 1, tensile yield strength should be used in calculations. And when strain rate is greater than 1, ultimate tensile strength should be used in calculation for allowable stress. From this, we were able to calculate mean time to failure for test vehicle 1 to be 19.5 hours, and for test vehicle 2, 34.4 hours. Now, the future work that we plan to conduct involves conducting failure analysis in order to find evidence on the migration from ductile fracture in the bulk solder in test vehicle 1 to the brittle fracture of the intermetallic compound layer in test vehicle 2. We plan to obtain appropriate level of magnification in order to observe the decrease in grain size of the cracked SAC-305 solder alloy, where grain size in test vehicle 1 should be greater than the grain size in test vehicle 2. We also plan to conduct test of failure harmonic vibration tests in order to generate stress-based fatigue curve and strain-based fatigue curves. In conclusion, we had presented in this presentation simplified methodology for microelectronics that were subjected to random vibration at board level, which is in combination of experimental and finite element techniques. Our goal was to provide consistent results for durability assessment of lead-free solder joints for high and ultra-high cycle fatigue that are found in the autonomous vehicle. The effectiveness of the proposed methodology was investigated for 2 test vehicles, and preliminary simulation versus test the failure results were presented. Finally, we would like to acknowledge participation of the following participants in the working group. Thank you.